So yeah, I wanted to give a little bit motivation for why we read this New Zealand document. It's a little bit old, but what I hope you got, and it seemed like you got from the summaries, from the questions, is that this document raised a number of questions that we're going to be looking at throughout the semester. For example, how do you map faults? How do you assign a different confidence to these faults? How far should different types of infrastructure be situated away from faults? And the US, especially California, has laws about building infrastructure near faults, which we'll hear about during the semester. But again, I picked this New Zealand document to introduce some of these ideas because it was quite easy, straightforward to read. And then, yeah, raise some of these other questions. So I'd like to begin with asking someone to summarize the paper as well as what the lasting impact was. So you can unmute yourself and speak up. Anyone like to jump in? You all turned in great summaries, so I'm confident that you read it.
I can go.
Excellent.
So my summary is that, so the planning for development on lands on or close to active faults outlines recommendations from geologists from many of the geological societies in New Zealand for districts in New Zealand to follow. The coalition proposed that councils in New Zealand take a risk-based approach for planning. Some of the key recommendations that they use are to identify active faults, create fault hazard zones, avoid building in hazardous areas, and mitigate the hazard when building has already taken place. And then the key components of the risk evaluation approach that they say are to take into account fault recurrence interval, fault complexity, and building importance category. And then they also go on to give case studies at the end of the document.
Thank you. Anyone like to add to that summary or offer a different perspective of the lasting impact of that document? Everyone is very shy this morning.
I guess the lasting impact could be that it provides a framework for other countries to use that have faced similar hazards.
Yes. New Zealand has been tested by many quite large earthquakes in the past 2 decades. It's also interesting to know how this document has evolved since then. All right, would anyone like to ask any questions? Or something you thought
I was going to ask how the some of the guidelines in the United States compare to the guidelines put forward by this document.
So in the US, the guidelines in California in particular are set by the Alquist-Purola law. And in particular, that many level of details, but it essentially restricts building within 50 feet of faults. And so that's fairly similar to the 20-meter distance in New Zealand.
I was wondering, I see that Richard has his hand up. I'm gonna wait.
Well, I just wanted to add to that discussion. So California is 50 feet from an active fault, but in New Zealand, they have sort of some stipulations in there that they can modify that distance depending on how wide and distributed the fault zone is. And so that's one difference between the two. So
So
I'd
does
like to
California,
sorry, I'd like to hear questions from you guys, but I have a lot of experience working with fault zone setbacks in California and different guidelines around the world. So I'd like to listen to some questions from you, and I may just intersperse a few things here and there.
Would you like to go?
Yeah, sure. So I was wondering how ahead of other countries were the policies in New Zealand? Like, are they at average level or?
I do not know.
They're pretty far advanced, really, and California was probably the first place to actually make the Criollo Act, in 1971, I believe. But really, it comes down to defining, if a fault's well defined, it takes studying to define the faults and map the faults. And so, a lot of countries are sort of behind. California and New Zealand are really kind of on the forefront. They have been on the forefront of, like active fault research for 30, 40 years. Other countries like Japan are pretty far along as well. But there's, some countries just haven't mapped everything in detail enough to have that sort of policy, and they haven't had that sort of initiative to do it yet.
Great, thanks.
Chris?
Yeah, I didn't have a chance to read the New Zealand document, but in California, the laws are usually in response to a precipitating event. So the Alquist-Priolo law came into effect after the early 70s San Fernando earthquake, which had surface rupture go through people's houses. And so that caught everyone's attention, and they created a law that there should be setbacks when you build houses near active faults. And this happened again after the Loma Prieta earthquake. There was an act that hazard zones need to be mapped, like liquefaction and landslide hazard zones from earthquakes. So that's how the laws have moved forward in California. I'm not sure if there were similar events in New Zealand that guided the generation of those laws or guidance.
Just keep in mind that the population of New Zealand is about 5 million. So it's the population of Phoenix. And so their number of people really to look at some of these issues and problems is much smaller than in the US. Ben.
I was just wondering, you've said before about how mapping the active rupture is not necessarily indicative of where a future earthquake rupture will occur. Do guidelines tend to take that into account at all, or do they assume that just the active fault trace you can see is all the hazard that there is?
That is an excellent question. And so in this, they map the fault and then they place that 20-meter hazard zone surrounding the fault. And they also discussed if the fault hazard should be larger if they map the fault as complex or distributed, or you might expect to have surface ruptures with fairly substantial offset outside of that 20-meter boundary. And we'll be focusing on that question quite a lot, and I'll just come back to it in a couple of minutes. Dominic?
I'll mute, go ahead.
So turn your mute on.
Just talk.
Okay.
We're having a computer feedback issue. Yeah.
Okay, so I was wondering who, oh my God, hold on. So I noticed that they sent out about 700 letters to property owners in one of the case studies, and I think only 65 people showed up. I was just wondering who has control to pass some of these policies, especially in some of these smaller communities, the smaller councils.
So your question essentially is, do the 10% of people that show up to these discussions kind of have outdue impact on the policy?
Yeah, because their feedback is what the council is taking into account when they're deciding what to do. I think it's the, the regional maps are made and then the district maps are made, and that's getting down to smaller, like our counties here in the United States, right? So counties have their own rules and regulations and policies, and so do states. And it just depends on where you are and what's been written for that particular county as to what you have to follow. But the majority of the citizens may not have a say, really, if it's a political thing, so it just gets implemented and then people have to deal with it. But it seems like in New Zealand, they had a pretty good, if your house was destroyed, you could still rebuild it if you were grandfathered in. I think in New Zealand, they have the benefit of a lot of open land. They call it green fields, I guess, that has not been developed yet. Places like California, there's a lot less open land. And so they're kind of a step ahead to get these planning documents on file so that, mitigation can be done for future development.
Maximilian?
Okay, can you hear me?
Yes.
Okay. So from what I understood is that New Zealand has a very highly decentralized set of planning regulations regarding development in fault surrounding. But how does that compare with other jurisdictions like California or, I don't know, the United States as a whole? Or maybe Canada or whatever? Like, how is it decentralized as well? Or because it seems there's no real strict framework. Like, well, that's what I understood in that paper.
Chris, would you like to answer that?
Again, I don't know what the framework is like in New Zealand, but I can bring it back to California. So if you look at a quaternary fault and fold database or fault activity map of California, you can find these online. It's not given that every single one of those faults is zoned as active. Under these laws, the state of California, the California Geologic Survey, is supposed to zone active faults. And to be active, they need to meet a couple conditions. They need to have ruptured in the Holocene, the last 11,000 years or so, and be sufficiently well-defined. There's blind thrusts, there's faults that are really distributed and they're hard to see in the geomorphology. Those usually aren't zoned. They may be zoned in the future if more work is done. But what the state geologist does is looks at, a fault that is likely active, studies may have shown that it's active, and does exactly what you're going to be doing. Does geomorphic mapping, looks at imagery, draws a bunch of geomorphic features on the map, and then defines the fault zone. And because that zone can have like a main strand and a bunch of secondary strands, the Alquist-Priola fault zone is going to be really wide, like thousands of feet wide. And then within that zone, if you're going to build a new set of houses or something like that, you have to do a study, like a fault trenching study, to make sure that your site, even if it isn't exactly on the main geomorphically well-defined trace, doesn't have a fault. And if it does, then you have to set back 50 feet. I've noticed in some areas you can negotiate on that a little bit. And then you're good to go. And if you don't find a fault, you're also good to go. But again, it starts with the regulating agency to define the active faults, zone the areas of interest that could have fault rupture related to that zone. And again, the most important thing, it's using the exact same tools that you're going to use in this class.
So one difference in New Zealand is they recognize an active fault as 120,000 years. So they just lump everything as 120,000 years and younger as, you know, suspect. And they don't have a Holocene criteria.
Right, I was going to ask you about that, Rich. So where is Nevada at right now? So there's California is super active, you know, high slip rate faults. So other areas that have lower slip rate faults may use different criteria. And I thought Nevada was looking at 125,000 years at some point.
We use 130,000 years as basically a datum, which is you know, quaternary geologic deposits that we can recognize that are of that time period, like lake shorelines and alluvial fans. It's kind of a good marker. That's, you know, we use that to say, okay, yeah, it's an active fault. But then they also have recommendations here at the state for Holocene active, similar. We're basically copying California and the 50-foot setback, but there's no legislative mandate to make that a law. But that's what we recommend, just kind of copying California's way of doing things for study. So it's a work in progress, and we'll see what happens. But in New Zealand, in this document that the students read, they kind of broke the faults up by recurrence interval. So everything younger than 120,000 years, but then if it had a really long recurrence, it had a different ranking than a fault with a really short recurrence. And so that may be a difference between California and Nevada also, because a lot of the normal faults here in Nevada have really, really long recurrence. So, you know, if you can demonstrate that it had an earthquake, you know, 5,000 years ago or 10,000 years ago, and the recurrence is 30,000 or something, is it really of societal relevance to zone a fault like that, as opposed to one that has faster recurrence intervals?
Right, and I wanted to add quickly that activity, this word that we're throwing around, it's kind of a regulatory construct. So activity under Alquist Priola is Holocene, 11,000 years. But for California Division of Safety of Dams, it's around 35,000 years, active fault that's of concern to a dam. For a nuclear facility, it's much longer. It's like 100,000 years. So keep that in mind when you use the word active. What does that actually mean?
All right, I wanted to just briefly share something from the text, and then we're going to move on. So this is an example of a surface rupture, and this is from an earthquake in New Zealand in 1987. And I want you to really just pay attention to what the surface rupture looks like, because we're not going to see that many throughout the course. We have this road here, and then we had 2 meters of offset along the fault, and we have this really, really sharp discontinuity along the road. And so here's the main trace of the fault, and then here we see that the fault steps to the right, and then in this section we have these subparallel sections of the faults. So here it's relatively more complex than in this section of the fault where there's one major trace. So yeah, just want you to keep some picture in mind of what fault ruptures look like. And you can imagine, so this earthquake was in 1987. So if we could travel back in time to 1986 and you're standing at this farm, what would this look like? You had an aerial photo. Could you draw a line where the fault is and anticipate the rupture? And so this is what we're going to be working on during the semester.
So it was exactly a question like that on one of the students' responses. How do you know a well-defined fault from hillshade images, you know, and LiDAR and stuff like that? So I mean, the answer is basically just look at this picture that Chelsea has up. There's a nice vertical scarp. If it would grow over, it would still be well defined. You could still see a shadow on it if you were highlighting it with a hillshade you could still see it in the field as a scarp, right? A scarp in the surface that goes continuously. That's kind of how you determine it's well defined. And I know we can't get to everybody's questions. The questions are really great to help us with discussion, but if there's something you really want to talk about with any one of us, just email me or drop into office hours or whatever, if there's ever a question from the reading that you want to discuss further.
All right, Ramon, quickly, and then we should move on. You're on mute. All right. Yes, thank you everyone for the discussion and for reading that assignment. So I'll hand it now to Rachel, who's going to discuss the geomorphic indicator ranking.
Yes, hi guys. I'm going to share my screen. Right, so today this presentation is going to go over the tool that you guys are going to be using and also future assignments. It's the Geomorphic Indicator Ranking System, or we call it the GIR. It's going to help you guys map the geomorphic features you see in the surface when you're completing your assignments, but it's also going to help you relate to how we'd like to then finalize the fault confidence ranking when you assign the fault, which is what we'll go over too in a bit. So what is the GIR? So it's a system that we use. We try to map the geomorphic indicators that we've been talking about, and then we try to quantify them in kind of a systematic way. And our hope of doing this is that we can find a repeatable way to rank our confidence with how certain we are of the fault location, and then maybe how active or how strong that trace is from the evidence just strictly on the surface. And so we'll rely a little bit less on some sort of like the preconceived notions that we have about an area that mappers, especially with more experience, tend to have. And I am like privy to it as well. If you look at the San Andreas fault, you're going to say, oh, that's a strike slip. So I know I'm going to see this, this, and this, but we could be neglecting other contradicting evidence that may lead you to a different conclusion if we already have that kind of notion in our head. And that kind of goes back to Ramon's point about how it's really nice that you guys are, he likes to use the word pure in the way that you won't be seeing the mapping environments beforehand or knowing any real information about them. So we're going to try and reduce as many of the external variables as we can to help provide the most like pure form of mapping. And like Chelsea mentioned, we worked on this last year. I led the development of this system because we were tasked with trying to find a way to create better pre-rupture fault maps. And it is kind of a system that a lot of industry geologists use, where they will use geomorphic indicators to try and map the faults, but that hasn't been done in a way where it's been like a accurate tool or kind of conglomerates everything together in a way that you can map them and then count them. And I think Ramon can put them in the chat too, but there are a few papers that talk about previous people doing this. There's a share where they developed a way to rank indicators, and then there's another paper by Salisbury and Zeke about it. And I think he might put the links in them, or I can put them in a little bit later. And so going back to the image we saw from Wells Creek, you could see that along the fault trace, there are some geomorphic indicator features mapped. They didn't count them, however, but you do kind of see how certain features along the fault trace come from a fault, and they're a bit indicative of faulting. But some of them also can be formed as a direct result of faulting. Other features that you'll see on the surface could be a result of other things. So you kind of get it in your head that some features are like, oh yeah, that's for sure fault. Some features can be a result of faulting, could also be a result of other geomorphic processes. For example, like the offset drainage that we saw in Wells Creek, there's no other way that could have formed other than faulting, but something like a linear trough or a linear ridge would be from faulting, could also be from other processes. And you will, when we work with our mapping, you'll see some of these in DEM, some of these features won't be visible in the DEM, but they will be visible in like pre-rupture Google imagery too, but you'll have access to both of those.
So let's take a pause. Christy has a question.
Yes.
Thanks. In older, like arguably active terrains, there's a lot of features that it could be like erosional along an older fault that get really convoluted, like an apparent drainage jog could be formed by the higher erodibility of the fault zone, so that like the drainage kind of finds it and creeps along it for a while before it takes its like preferred gradient. And so it creates this like ambiguous space in Canada in particular. It's a big problem in Canada where there's like very old structures and a lot of reactivation. Which is not a question, but my question is like, you know, do you have to come up with like a custom series of metrics or features for each site? Are things transportable?
Yeah, so, and I'll talk a little bit more about it too, like the nitty gritty of the GR, but we do take into account the preservation of the feature, because in more desert or dry climates, the features are going to be preserved a lot better. And then in an area that is humid or is prone to erosion with a lot of vegetation, the features aren't going to be as strong. But it also takes into account when you're doing the GIR that in an area where there just aren't that many features available, when you do find a feature, when you do the calculation, it will still take into account that that is the strongest feature, albeit that there are going to be a lot fewer of them in that landscape as opposed to like something along the San Andreas.
Okay. So there's this competition between like the geomorphic forcing of the fault versus the surface processes basically that are like in the background.
Mm-hmm.
But we are still working on really making it like fully comparable or transportable, as you said, between different areas.
Mm-hmm.
Yeah.
That's been one of like the larger challenges of trying to make this a super comprehensive tool.
Cool. Thanks.
And the more features that you can find along strike, you kind of get more and more confidence as you go, you know. So in areas where there's a differential erosion or something and you're kind of confused, but if you see other features that are fault related along strike, then you kind of get more confidence that you're along the fault.
Right.
Yeah, I'd second that. So I always map keeping context in mind. If I find one really good feature, I will continue walking or mapping along the fault. And if I find a bunch of similar features, as Rich said, I get more confident. Sometimes with those old erosional features, you'll have a few good features, or just like, I don't know, a linear drainage, something like that. But it won't continue for many kilometers. You know, then you'll run into other things. Or another thing to consider is just deposits. If you've got a recently active fault and you've got some younger alluvial deposits, those should be impacted by fault deformation. So you want to keep the age of the materials in mind. Make sure that you're not just mapping your fault all in bedrock. Try and extend it across some younger deposits and see if there's any impact on those.
I have more questions, which I can save, but
Rachel, keep on going. So we
sorry. Okay, I'll save it. Sorry.
It does also like pose the question too, if you do find something super eroded and old, but it is a fault feature, does that mean it's going to be an active fault trace, or is it just from a really historic earthquake? And we'll look at an example of that too from one of our mapping areas that we've done in the past. And I'm going to show you guys just kind of a slew and some images that you can get your eyes on of geomorphic indicator features that we have. I won't include all of them that we will provide to you because there are quite a few, but just some examples so you can get an idea of what they look like in the surface when you're mapping them. Okay, so this is a photo of an alluvial fan from a mountain range in China. And I wanted to just kind of pose the question out to you guys before we move forward, if anyone wants to annotate it, or if they think where the fault trace is, or what kind of things they're seeing on the surface that would indicate faulting. And you can type it or just say it, just whatever you think. And if you don't know, that's fine too.
So in class here, yeah, the discoloration across the fan here.
And then Aaron drew a trace right there, which is good. Yeah, so the main things that will stick out, especially in alluvial fans, will be something called a surface unit offset. And you'll see that in, yes, nice Maximilian. And then I kind of just drew like a really like simplified version of where the fault may be and where the offset occurs. And so the ones that we could see here for the units are going to be a surface unit offset. You'll most likely see these in quaternary or younger sediment deposits where you could see the darker and the lighter ones, they should match up had the fault not gone through it, and that lower right hand would match with the upper left one. But if we were to analyze it a bit more and you could see a bit closer, you'd probably find some uphill scarps too from where the fault trace ran across. So you know that the original deposition order of them is disrupted in a way, it's unnatural. So there's probably something else happening here besides the normal fluvial processes. Yes, Rich.
Yeah, so Ramon put in the chat, try to map the indicators first before you draw the line on there, right? So we want to think about process, and so we all pretty much saw the linearity and the tonal contrast in the linear fashion across the fan, but think about process and how those fan deposits are coming down, and they have a really markedly different sort of channel form when they get across the fault. So, those skinny beige lines down below, there's a big change in what's going on and how sediment and water is moving around. So you want to kind of pick out some of these things before drawing the line, and the indicators you're talking about. Add them to the map first.
Yes, yeah. And because before I started getting into the GIR, the first thing many people look for faults is going to be lineation. But we are trying to use this tool to try to dig a little deeper apart from the lineation and find specific features that can give more direct evidence to the faulting location. And then our next one, these are called triangular facets, and it shows it kind of in a simplified version on the right side, and then on the left side what it would look like from an oblique view on satellite imagery. And they normally form at the base of mountain ranges at the front, but they can also be formed on the sides of river valleys if there's erosion and down cutting. So in that case, it would not be from faulting. So this feature requires a higher level of analysis to determine whether or not it is a triangular facet, if it is a result of faulting. And they, going back to Christy's point, the level of erosion can vary from these. So on the bottom, they are very pronounced and probably a bit newer. And then on the top, they are a bit more eroded and the triangles are more rounded towards the back and they aren't as prominent. Does anyone have any questions about the triangular facet?
Could you draw on it and show us where the faulting is?
So these guys right here will be the facet. And so they are normally bounded by the outgoing drainage channels right here. And so you'll have drainages coming from either side. And as the fault drives along the base of the front, you'll see that there's kind of a lineation right here that stops the mountain front from progressing. And the same goes for right here as well. You'll see there's kind of an abrupt stop toward the progression of the mountain front. And you will also find some scarps too at the base where the fault plane has dropped the base of the ground.
And then another feature that goes along with triangular facets is wineglass canyons. So the canyons get wider going up slope. And then when you have a faulting event along the range front that steepens up the range front, that's the stem of the wineglass will erode and in size through the new fault scarp. And so that's a feature that we see pretty commonly in wineglass canyons.
Mm-hmm. And they'll kind of, I'm trying to draw a really bad version of it, but it'll sort of look like that on the surface too. next, and so we're going to go and see if we can look at some more on hillshades too in DEMs, because there will be some that are going to be more apparent on the hillshades and some that will be more apparent on the Google imagery. So this is an example of a scarp, and they can either break through the older bedrock surface or the younger. It does also require like a little bit higher level of understanding, and I'll annotate where it is as well. So if you could see right here, there's the abrupt change in slope right there. Again, it could also be a result of other geomorphic processes that can result in an abrupt change in slope, but if you can identify the scarp correctly, it's almost certainly a result of active faulting. And this one is quite preserved well, but there are going to be times where sediment starts to flow over it. But like Rich said, if you kind of change, you can still see the shadows of the hillshade and still have it be apparent. Do you have another question, Rich? Okay.
Oh, go ahead. Thanks.
And so a quick and dirty like fault trace of it will be right there. You can also, if you can identify some glacial moraines down here, it's nice. It doesn't necessarily indicate active faulting, but they are there. And then this is called a shutter ridge. So this is when it's normally formed by strike slip environments, but a normally formed ridge, when the fault cuts through it, it'll kind of drag the ridge along and create either offset the ridge, or it'll cut the ridge and make a very like pronounced linear form on it. And it does often result in like a deflected stream. It can make a valley if it's next to the valley linear as well. So you'll find that some features are going to be in junction with each other. So if you find one feature, you might want to look for others that relate it in the same process.
Could you annotate this image as well?
Yes, it is right there. And so the ridge that is getting cut across is this one. It might have looked more rounded at the end, or it could have even gone all the way over there. But when the fault cut through it, it could have broken the surface, and the area that was disrupted by the fault could have eroded out and then gone with the deflected stream. But the deflected stream, you could see, cuts all the way over there too. It will be more visible in a hillshade as opposed to on the right side where they did kind of a mesh of a colorized slope and Google imagery.
So Ramona is reminding us that when we're doing this mapping, I want to start with thinking about the landscape and these different indicators before drawing the line of the fault.
Mm-hmm. Yes.
And the GIR, really the point of it is it really forces us to do this geomorphic mapping before drawing the fault lines.
Mm-hmm.
Yeah, and I'll underscore that as well. So if I'm mapping a fault for a pipeline fault crossing, I definitely won't start with the lines. I'll start with a bunch of points along where I think the fault is, and I'll mark deflected drainage, linear valley, sag pond. I'll just put a bunch of points, see if they align. If they're just scattered all over the place, then they may not be related to faulting. And then I see if I can build an argument for a fault going through that area based on the different lines of evidence that I found.
Mm-hmm. Perfect. And then this is just a pretty large list of all the indicators you may find. It doesn't include all of them too in the list, but it just kind of gives you a slew. You don't have to memorize all of them now. We're also going to provide you guys with a document that lists all of the features with their description and their justification as a fault indicator. But we encourage you guys to read through other text or through the McAlpin as well to find any other ones to learn about the features.
These are covered in McAlpin, so we'll talk about them, but they'll also be in the readings in the next few weeks.
Yes. So now when we were developing the system, we were trying to find a way to quantify the features and then how that would relate to how strong our confidence would be of the fault location, or how strong that certain trace is in relation to all of the features that we're seeing. So we thought of a 1 to 4 ranking. And so with 4, that's going to be the strongest evidence for faulting. When we have features with that ranking, it's like pretty unequivocal that it's going to be from tectonic activities. So that's going to be like your offset drainage or a quaternary scarp in relation to other features. And then it just kind of progressively goes down, with 1 being that it's little evidence of faulting. Features that have a ranking of 1 could result from faulting, but if it's a standalone feature and it's not in junction with other stronger features, then it's likely a result of other geomorphic processes. We think of 4 as like the gold standard too. So whenever we map them, you won't see, they're going to be a bit more rare, and they're going to require a higher level of analysis in order to ascertain that it's going to be that feature. But we also, when we started to develop this, we saw features that they didn't really even fit into the 1 ranking, but when we would see them in the surface, they could indicate faulting, but they could also be a result of other processes, even less so than a feature of a 1 ranking. And so we decided to add this thing called a modifier to the system. And so they're only to be mapped when they are near where the proposed fault is, and if they're around other around other higher ranking features. And so there are positive and negative ones. So positive ones fortify the presence of the fault, but if you map them as a standalone feature without any other surrounding stronger features, then it's unlikely that it's going to be a result of faulting. But then we also have negative modifiers, and those are meant to be used when the presence of them near the proposed fault reduces our confidence of the fault location. And those things include like erosion, like Christy was talking about, and then anthropogenic alteration, which is pretty much anything that humans put on the surface to obscure evidence of a fault. So it could be roads, man-made water surfaces, urbanization, farming. And then something interesting too is we have landslides as both a positive and a negative. So landslides occur because of coseismic shaking, so they can indicate the presence of a fault nearby, but they could also obscure other fault evidence on the trace if it's covering the scarp or it's covering a beheaded drainage. Do you have any questions about the feature ranking or the modifiers so far?
Could you give an example, Rachel, of what is like what would give us a score of a 4?
Yeah, so if we were looking at a strike slip fault with a offset drainage, we would map the drainage as a score of 4. It's unequivocally a result of faulting. But let's say a little bit further down, we see a linear, just like a lineation or a vegetation lineation, some kind of like visual lineation in the surface. We can mark that as a modifier, but if it's right next to a beheaded drainage with a score of 3, then that would bump up that score for that area. But I'm going to also show like a step-by-step too. I'm going to walk you through like an example of how all the scoring works.
Is there a difference between an offset drainage, which just has a really sharp offset, you're really confident that it's related to a fault, versus a deflective drainage, which could be just something that forms naturally away from a fault? So are those different indicators?
Yes. Yeah, we have the deflected stream or drainage will have a lower score than the offset drainage.
Great.
I think it's like a 2
or 3. Yeah, it's definitely lower.
And so I'll show you some examples of modifiers now that you'll see on the surface on hillshade and optical imagery. So this is an example of what a landslide might look like on a hillshade. This is from Kaikoura, New Zealand. And so in one way, it can indicate a nearby fault, but in another way, it can also obscure it if it were to cover the fault trace. And I've mapped out the extent of the rough extent of the landslide for you guys. So you can see that it has a rougher surface. The surrounding hillshade is going to be a lot smoother, but this has a bit more rugged terrain and it is confined to a certain area. And if we were to then afterwards, like do the rest of the geomorphic mapping and place the fault trace relative to the landslide, this is where I had placed it a while ago. And then another example of a modifier. Yeah.
So in that last example, Rachel, you can say that landslides can have a plus or minus score. So in this case, what would you give it and why?
Yes, so I would give this a positive score. It's not obscuring the fault trace. And also in Kaikoura, New Zealand, there is fewer features. It is a reverse faulting environment. So you're going to have less geomorphic features to find, and there's a lot of vegetation. So when you do find the geomorphic features in areas with a lot less of them, you do want to try and score them as such. So if I did see a landslide in the surface and it's not obscuring an obvious trace, I would use it as a positive.
And where would you put your point marker for this landslide?
Yeah, you can either put it in the middle of the feature first when you're mapping it, or you can put it closest whenever you're trying to actually implement the GI, or you can put it closest to where the proposed fault trace is as well. But if
go ahead, sorry.
Sometimes the features will be large enough that when we segment our traces to count features, it could, like our fault trace segment could end right there. So it would be counted twice in that case, because it is going to be here and here if it's large enough to do that.
Could you discuss how you mapped the landslide here? And kind of what some of just that noise or that like really roughness in the data is?
Yes, oh, like above and like right here.
Well, yeah, some of those do look like the landslides also, or the like headscarps.
With this data, I believe it included vegetation, or they tried to remove the vegetation. So oftentimes when you're trying to get the data that just has the surface, the vegetation can still obscure a bit and give you this kind of blocky appearance. So it may look like really blocky and rugged terrain, but it also could just be an artifact from how the data was collected. So if I see a bunch of this kind of blocky terrain everywhere on the surface, I can assume it's a result of the raster and the way the data was collected.
Can you go back slide, Rachel?
Yeah.
I think they want to see the area without the green.
Yes.
Yeah, so some of the discussion in class here has been like, you know, it's hard to map landslides. The difference between smooth and kind of more drainages on the hill slopes can indicate sliding. It may be an older slide or a slide face of some kind, because we're not really seeing a deposit that would have come from there down below, you know, so it may be an older landslide. But yeah, we realize that this is just, you know, illustrating, you know, looking at landslides, but mapping landslides is tricky.
And it is often that it might not.
Do you know what this approximate scale bar is on this, Rachel?
I want to say this is 250 meters is what I was
the length.
And yeah, they could also result from many other things besides faulting. So that's why we give it just kind of like a 1. If the landslide were in a location with a bunch of other geomorphic features, we could kind of lead to the conclusion that it's a result of faulting. But if it's a standalone thing, there's nothing else around it, we can kind of write it off that it's not an active fault indicator.
Okay, maybe we should, it's lots of good questions. Maybe we should keep on going because we do only have 15 minutes left.
Okay. And hopefully when I go through the example, it'll be a lot clearer of like where we put the points and how everything is sorted. So this is quickly another modifier. It's a vegetation lineament. This can happen when the fault runs through and breaks the soil surface beneath. So one side is able to have more vegetation growth than the other. This is another one where it could just be a result of preferential vegetation growth based on the soil, but here it's very stark and it's along the San Andreas fault. So you can likely see it, but again, it won't be a very strong indicator. So it's just a modifier if you see it with a bunch of other stronger surface indicators.
Can you also just show how you would map or where you would put your points?
Yes. So if I was segmenting my traces and this is the length where like the fault would run along, I would put the lineament along here with whatever, like, because we will end up showing you how that we segment the faults and count the features. So if the segmentation of the fault went like this, I would want to count it everywhere I see the feature along the segments.
And so again, you would put those points that show the vegetation lineation before you mapped the fault.
Yes.
And then
Yeah, and on this one you might say, you know, it looks like a little bigger in the north or on the top right up there than it does down below, like, or the lineament's stronger, you know, vegetation lineament's wider. There's these sort of, you know, qualitative ways we think about it, right?
Yes. So geologic context can interfere or make some of these interpretations more difficult, and that's one reason why there's this lineation in the vegetation it's a modifier with a score of +1. It's quite a weak indicator, especially without other strong indicators. So it alone is insufficient.
Mm-hmm. And I just wanted to show the effect of urbanization and erosion that can have on the hillshade. So there's a lot of urbanization, farming, roads, and vegetation on this hillshade. So it will be, I could just show you how difficult it can be to kind of suss out some of the features. I'm gonna cruise past that. We also wanted to go over the distinction between primary and secondary faulting when you guys are gonna have, yeah.
Pause. I think we're slight change topic. Should we pause for a couple minutes for questions? Mara? Do you have a question?